Okay, students, Assalamu alaikum. Last time we were discussing about, or we were covering the topic of momentum principle in fluid mechanics, where our main objective was to study the fluid kinetics in terms of the momentum changes that occur due to the fluid flow, due to the motion of the fluid. Anyway, so what we did was that we first of all used the Reynolds transport theorem and used momentum as an extensive property in the Reynolds transport theorem and developed the momentum equation for the fluid flows. Okay, and the momentum equation that we developed for the fluid flows was this one. So this is the three-dimensional linear momentum equation, which we developed for the case of the fluid flows, that involves the forces and the momentum of fluid flows in the x direction, y direction, and z direction. And then we continued with it for solving the momentum equation to some of the common applications. Normally for the case of jets, the fluid jets, we solve the problems related to the fluid jets. Now, today, what we are going to do is we are going to continue with our analysis and we are going to move towards another application of momentum flows, fluid flows, or the momentum analysis within the fluid flows in case of the nozzles. Now, first of all, what is a nozzle? Nozzle is basically a form of a pipe. Okay, but this is a pipe which is of decreasing diameter. Okay, so we'll have a pipe, and in such a way that the diameter of the pipe is decreasing. So if we have a pipe with a decreasing diameter, then this is known as nozzle. The fluid flows in it. Okay, and as the fluid flows within the nozzle, obviously the velocity of the fluid increases. Most of the time we uses the nozzle whenever we want to have an increased velocity of the fluid. So the assumptions made about fluid flow through a nozzle are itemized as below. The velocity is uniform across section A and B. So for example, this is a nozzle from A to B. At any section, the velocity is uniform. Okay, velocity is uniform means the velocity is not changing from point to point within that section. Then if the nozzle exhausts into the atmosphere, the pressure at section B is atmospheric. So suppose at this point it is going out into the atmosphere. So at this point, the pressure is atmospheric. That means the gauge pressure is 0. The Bernoulli's equation is applied between sections A and B. So at the inlet of the nozzle and at the outlet of the nozzle, or between any two sections of the nozzle, we can apply the Bernoulli's equation to obtain the pressure at A. The pressure will exert a force of magnitude PA. So whatever the pressure will be there at A, corresponding to that pressure, the force of the fluid will be exerted over the nozzle at this point. Okay. So since we know that pressure is force over area, so in this case, the force of the fluid will be pressure multiplied by area, and that will be exerted at this point. Okay, where P is a gauge pressure at the centroid of the section. Obviously, where it will be acting exactly at the center of this section. So these are some of the assumptions for the solution of for solving momentum equation in the fluid flows for the case of nozzle. So let's directly move towards the problem and try to solve problems of fluid flows related to the momentum equation. So the sketch shows air flowing through a nozzle. So this is a nozzle here. Okay, this is a nozzle here, and air is flowing through the nozzle. So the flow is of air. Okay, air flowing through the nozzle. The inlet pressure is 105 kilopascal. So this is 105 kilopascal, and that is basically the inlet pressure, means at this point, point 1. Okay, and the air exhausts into the atmosphere where the pressure is 101 0.3 kilopascal absolute. Now here one point is very important, that in our analysis, in our calculation, wherever we will be solving the problems, we will be using gauge pressure, not the absolute pressure. Now here the pressure P1 given is absolute, and P2, which is at going into the atmosphere, that the atmospheric pressure is also given in absolute terms, which is 101.3 kilopascal. Okay, so that is at 0.2. So anyways, whenever we will be solving the problem, we will be using the gauge pressures, not the absolute pressure. So if the atmospheric pressure is given, then we can simply calculate what will be the gauge pressure. So the nozzle has an inlet diameter of 60 millimeter. Okay, so that 60 millimeter is the diameter at the inlet. So this will be at 0.1. Okay, and an exit diameter of 10 millimeter. So 10 millimeter is the diameter of the nozzle at the exit. That will be at 0.2. And the nozzle is connected to the supply pipe by flanges. Obviously, these are the flanges through which the nozzle is connected to the main supply pipe. Find the airspeed at the exit of the nozzle. So we need to find what is the airspeed, V2 at the exit of nozzle. We need to find what is the airspeed at the exit of the nozzle and the force required to hold the nozzle stationary. Okay, the thing is that we have a main pipe and a nozzle is connected to the main pipe. Now, when the air is going to flow through the nozzle, it will try to push the nozzle out. Okay, now in order to keep the nozzle connected with the main pipe, we need to connect the nozzle with the main pipe using the help of flanges, and flanges are bolted together. So practically, flanges are holding the nozzle with the pipe in this connection. So obviously, there will be force required to hold the nozzle in place when the fluid is flowing through the nozzle. So we need to find out how much is the force that is applied by the flanges to hold the nozzle in place. Okay, so this force, the force needed here, is also needed to be find out. Assume the air has a constant density. Suppose the density of the air is provided and it is constant. Neglect the weight of the nozzle. So this is the problem statement, and so we need to find the force and we need to find the velocity at the exit of nozzle, velocity of air at the exit of nozzle. Okay, so this is the problem statement. We have a nozzle here connected with a pipe, obviously held together with the help of flanges, and the pressure at the inlet of the pipe, absolute pressure is provided. The exit of the nozzle is going into the atmosphere. The atmospheric pressure, absolute value, is also provided. Okay, the diameter at the exit of the nozzle, at the inlet of the nozzles are provided. And we need to find, since the air will be passing through the nozzle, what will be the velocity of the air at the exit of the nozzle, and the density of the air is provided. Okay, and how much force will be needed to keep the nozzle in place. Since we are talking about here fluid kinetics, so the force factor is important, that needs to be given in the consideration. So this is the problem statement and the figure. If there is anything within the problem statement or the figure which is not clear to anybody, please feel free to ask. If the problem statement and the figure is clear, then we will move towards the solution. Okay. So since I have a brilliant class, so that is good that everybody understands everything. Okay. Let's move towards the solution. Whenever we need to go for the solution, the first thing is that we need to draw the free body diagram. So we'll have a free body diagram of the force diagram and the momentum diagram that we are going to develop here. So let's have a look at these diagrams. Force diagram. So here we have the nozzle. This is the nozzle. So you see the dotted lines. This is our control volume. This whole dotted line region is our control volume. Okay, so in this control volume, first of all, because the fluid is entering into the nozzle from the pipe, so there will be the pressure in the pipe. So corresponding to the pressure of the pipe, we are going to have a fluid force which will be acting on the inlet of the nozzle. So we are going to have a fluid force due to the fluid flow. Okay, so that will be the first force which will be there at the inlet. Then at the exit, we won't have the force. Why? Because at the exit, it is going out into the atmosphere. Since it is going out into the atmosphere, we are assuming that since we'll be using the gauge pressure, so at the exit, the gauge pressure is 0. So if the pressure is 0, correspondingly, the force is also 0. Okay, so there won't be any force of the fluid at the exit. Then we will have the force by the flanges to hold the nozzle in place. So we're going to have this force. So basically, two forces are there. Okay, one is this force of the fluid flow, and the other is the force of the flange to hold the nozzle in place. Other than that, we can also have the weight of the nozzle. And if the weight of the nozzle is there, it should be acting in the downward direction. But let's see the problem statement. It says that neglect the weight of the nozzle. So if you neglect the weight of the nozzle, then the weight of the nozzle is not there, obviously. And then we can also have the weight of the fluid inside the nozzle. It should be also acting downward, but we are also neglecting it. Although it is not mentioned here in the problem that we are neglecting it, but it is understood why, because if we were not neglecting it, then we should know what is the volume of the nozzle, so that then we can find out at how much is the weight of the fluid in the nozzle. But since the fluid is air, and we know that air is very light compared to water or any other liquid, you can see that the density of water is 1000 kg per meter. The density of air is 1 kg per meter, like about 1000 times less than the water. So since the air is very light, so probably we can also ignore the weight of the air. We are already mentioned, it's already mentioned in the question that neglect the weight of the nozzle. So we are neglecting the weight of the nozzle as well as the weight of the air. So there won't be any force or any weight acting in the downward direction. So when we are making the force diagram, so in the force diagram, we have only these two forces, and that's it. So now let's talk about the momentum diagram. In the momentum diagram, we don't show the forces, we just show the flow going in, flow going out, and correspondingly the momentum of the fluid. Okay, so we have the fluid going into the nozzle, and then we have the fluid going out of the nozzle. Okay, so into the nozzle is mv1, out of the nozzle will be m dot v2. So into the nozzle is m dot v1, out of the nozzle is m dot v2. So these are the momentum. So now that's it. We have made the momentum diagram and the force diagram. Is the momentum diagram and force diagram clear to everybody? If anybody have any question regarding these diagrams, let me know. Now the thing is that we have so if you look here in this problem, we have no momentum, no force in the y direction or z direction, just one direction forces, one direction flow. Okay, so we are going to use the momentum equation only in the x direction. So we are going to just use the x component of the momentum equation only. Okay, now if you look at the x component of the momentum equation, okay, so let's have a look at the x component of the momentum equation. This is the x component of the momentum equation. Now here, what do we have? We have forces here. We have this is the accumulation term. Accumulation term always will be 0, because in this case also we have a nozzle, but the nozzle is neither moving nor the nozzle is expanding or contracting. So there won't be any momentum accumulation term. Okay. So in this case, momentum accumulation term will be 0. Now we will have the momentum flow going in, momentum flow going out, and it all requires velocity. Velocity of the fluid going out, velocity of the fluid going in. Now the question is that, do we have velocities in this problem? Now if you look at the problem statement, we have inlet pressure, we have outlet pressure, we have the inlet diameter, we have outlet diameter, we have density, no velocity at all. So if we don't have the velocity, it's not possible to solve the momentum equation because it requires velocity. So the thing is that now what we are going to do is that first we are going to use the Bernoulli's equation to find out the velocity. First we are going to use the Bernoulli's equation to find out the velocity, and then after that, once we have the velocity, then we are going to jump over the momentum equation to solve it. Okay, so this is the main idea. So if we apply the Bernoulli's equation, obviously it was said within the assumptions of the nozzle. If we go back just to the Bernoulli's equation can be applied. This is one of the assumptions of the nozzle. We can apply Bernoulli's equation here. So if we apply the Bernoulli's equation, so this is the Bernoulli's equation. That's how we apply it. Okay, that will be between 0.1 and 0.2. Okay, so this is applied in the form in the pressure format. Okay, so we have P1 plus gamma Z1 plus half rho V1 square. So we have hydrostatic pressure at 1, pressure due to elevation, and then kinetic or dynamic pressure at 1 equals to P2 plus gamma Z2 plus half rho V2 square. This is the Bernoulli's equation. Now, first of all, this nozzle is there in the X direction, and probably the X direction is the horizontal component. So if it is horizontal component, so at 0.1, which is the inlet, and 0.2, which is the outlet, there won't be any difference in elevation. So elevation is same. Whatever is there at 1 will be the same at 2. So this term, gamma Z1 and gamma Z2 will cancel, because Z1 is the same as Z2. Okay. The other thing is that it is mentioned in the problem that the air exits into the atmosphere. So at 0.2 we have atmospheric pressure. Okay. So at 0.2 we have atmospheric pressure. Since we will be using the gauge pressure, so P2 will be 0 as well. Okay. So P2 will be 0 as well. Okay. I'm not saying gamma Z2 is 0. I'm not saying gamma Z1 is 0, but I'm saying gamma Z1 is equals to gamma Z2, so they cancel each other. Okay. So there, the net effect is 0. Okay, but P2 is 0 because it is going into the atmosphere. Atmosphere gauge pressure is 0. Okay, so what do we left up with? We have P1 plus half rho V1 square, and here we have half rho V2 square. Okay, density is known in the problem. Okay, pressure P1. Okay, what pressure is known here? We know P1 is 105 kilopascal absolute, but I told you we are not going to use the absolute values. We need to use the gauge values. So gauge value would be what? So P1 gauge would be equal to P1 absolute minus P atmosphere. Now, atmospheric pressure absolute is given as well, where the pressure is 101.3 kilopascal absolute. This is the air exhaust into the atmosphere where the pressure is. So we know P atmospheric pressure, and we know P1 absolute. So we will use it to find what is P1 gauge. Okay, so P1 absolute minus P1 atmosphere, that's 105 minus 101.3. So that will be something 3.7 kilopascal. Okay. So this is what it is. So we will get what is the P1 gauge. So that means we have P1 gauge with us. Okay, so coming back over to the equation, P1 is something that we have. There's 105 minus 101.3, that's about 3.7 kilopascal gauge. Okay, so this is we have. Okay, V1 we don't have, V2 we don't have. So what do we have here? We have now an equation where we have two unknowns. We don't have the velocity at the inlet, we don't have the velocity at the outlet. Okay, so that means this equation could be useful, but not enough to find out the velocities. We need another equation where V1 is connected with V2, okay, and so that then we can use the two equations simultaneously to solve the problem. So the most common equation that we can apply here is the continuity equation, the conservation of mass flow rate. Okay, so that conservation of mass flow rate says that we have mass flow rate at the inlet should be the same as the mass flow rate at the outlet. Or the formula for the mass flow rate is rho A1 V1 will be equals to rho A2 V2. Okay, so now the thing is that density is the same at the inlet and outlet because it is the air which is flowing through the nozzle from the inlet to the outlet. Since the density is same, so density is going to be cut here. Okay, and what is area? Area is the cross-section area of the nozzle at 1 and 2. So it's basically circle. Okay, so because nozzle is a circular cross-section, so area will be pi by 4 d1 square v1 equals to pi by 4 d2 square v2. Now thing is that pi by 4 will cancel. We get another equation where we are connecting v1 and v2 together. So that's v1 d1 square equals to v2 d2 square. So now we have two equations, two unknowns. d1 and d2 are the known. We know d1 and we know d2. So v1 and v2 are unknowns. And we have this another equation where v1 and v2 are unknown. So now we are going to use these two equations simultaneously. So the way will be that we find, let's say we find v1 from this equation, substitute it into the other equation, and then find v2. So the formula becomes like this. When solving it for v2, we get v2 equals to 2p1 over rho 1 minus d2 by d1 power 4 under root. Okay. So here we know all these variables. We know p1, we know density, we know d2, d1. So we can find what is the velocity v2. And once we have velocity v2, since we already have the relationship between v1 and v2, okay, so we can use any of the two equations that we have and substitute the value of v2 to find out what is v1. So v1 comes out to be 2.16 meter per second. So now what we have done is that we have found out the velocities by using the Bernoulli's equation and the continuity equation together. Okay, our problem is not solved yet. We have just find out the velocities. Now we are about to start solving the problem using the momentum equation for the fluid flows. So the momentum equation for the fluid flow is this. This is the momentum equation for the fluid flow. Let me just erase this. This is the momentum equation for the fluid flows. So we have summation fx equals to d by dt integral vx rho dv, that's the accumulation term, plus summation of m dot out vox minus summation of m dot ivix. Okay, so first of all, accumulation term will not be there at all. So we are going to cancel the accumulation term. Let's talk about summation fx. So we have two forces here, F and P1A1. Okay, so since we have put the direction of both the forces in the positive x-axis, so here it will be summation fx will be F plus P1A1. So this will be summation fx. Now let's talk about flow in and out. Okay, so flow out will be m dot v2 and flow in will be m dot v1. So we have one inlet and one outlet. We already know what is v2 and we already know what is v1, but we don't know what is m dot, but we can find out. Okay, how can we find out m dot? Because m dot is rho a v. Okay, so if whether we take it m dot 1, it will be the same as m dot 2. It will be the same as m dot. Okay, so if we take 1, then we should use 1, 1, 1. So we know the area 1 because we know the diameter at inlet. We know the velocity at the inlet. We know the density. So we can find out what is m dot. Okay. So m dot is something clear. Now, once we have this thing, now we can apply it into the main equation. Okay. This equation. If we apply it into the main equation, we're going to get this thing. Now in this thing, we have everything. We just substitute the values and we're going to get the value of F. So the value of F comes out to be negative 9.9 Newton. Negative 9.9 Newton means our assumption for the direction of force of flange is wrong. And that makes sense because if you look here, this is the nozzle and it is attached with the pipe and the flow is going like this. So the flow is trying to push the nozzle out in this direction. And in order for the flange to keep the nozzle in its place, flange must be applying force in this direction. to keep the nozzle in place. Okay, so it should be in the direction opposite to the flow. Okay, so previous assumption was that the force of the flange is in this direction, in the positive x direction, but our assumption was wrong. Correspondingly, the value of F comes out to be negative, and that makes sense. Okay. So that's negative 9.9 Newton. And with this, we have solved the problem. Now, if there is anything within the solution of this problem which is not clear, so kindly let me know. So we were required to find two things: velocity at the exit. This is first we have find out using the Bernoulli's and continuity equation, and the next thing was finding out the force required to hold the momentum in place, required to hold the nozzle in place. So if there is anything within the solution of this problem which is not clear, please feel free to ask. This is good that everybody is understanding everything. Let's move over to the other problem. Okay, we have an engineer who is designing a water toy, is making preliminary calculations. A user of the product will apply a force F1 that moves the piston at a speed of 300 millimeter per second. Water at 20 degrees centigrade jets out of a converging nozzle of diameter 15 millimeter. To hold the toy stationary, the user applies a force F2 to the handle. Which force F1 versus F2 is larger? First of all, you need to answer that. And then you have to explain your answer using the concepts of momentum principle. And then calculate F1 and F2, neglect the friction between the piston and the wall. First of all, this is basically a syringe. This is basically a syringe. If you look here, the toy which is mentioned here is basically a syringe. So if you look at the syringe, now what do we do? We use it like this. We hold the syringe between our two fingers, and then we push the plunger with our thumb. Now, when we are pushing the plunger with our thumb, our two fingers are actually holding the syringe in place. So the thumb is actually moving in one direction, and our fingers are pushing it in the other direction to hold the syringe in place. This is what's happening. Suppose if we do not apply the two fingers, if we just apply the thumb force, what will happen? The plunger might not be pushed. Why? Because the syringe will move. In order to keep the syringe in place, we have to apply a little pressure with our two fingers to keep it in place. Okay, if we don't apply the two fingers, then the whole syringe will move. It will not push the plunger. Okay, so this is what happens here. Here, instead of, because this is a big syringe, so a hand cannot hold it. So what they do is that they put a support rod here, and so you can hold the support rod and push the plunger. Hold the support rod and push the plunger to push the piston in the syringe. Okay, so this is how it is. This toy is, so you have a plunger and you are pushing. So when you are holding the plunger, so you are pushing the plunger towards yourself, but while you are pushing the piston, you are pushing the piston away from yourself. So we are applying two forces. One force to push the piston, the other force to hold the plunger in to hold the syringe in our hand. Okay, from the rod at the bottom, from support rod at the bottom. So we are applying two forces in the opposite direction. Now the first thing is that which force is greater? The first question is that we are applying two forces. One force is F1. F1 is the force applied on the piston of the plunger, and the other force is F2, which is applied to hold the syringe in place. Okay, so for the first question is that between F1 and F2, which one is greater? And then explain your answer using the concepts of momentum principle. Then calculate F1 and F2, and then we have to actually calculate how much will be the force F1, how much will be the force F2. Okay, and we have to neglect the friction between the piston and the walls. So the diameter of this cylinder is basically capital D, and which is actually 80 millimeter. And the diameter of the jet, which is coming out of this syringe, is a small d, which is 15 millimeter. This is also provided. Okay. And we are given what will be the speed of the piston. Speed of the piston is given, which is 300 millimeter per second. Okay. So that's all. And we need to find out, first of all, we need to find out what are these two forces. I mean, which one is greater, which one is smaller, and then we need to actually calculate how much is F1, how much is F2. This is what we need to find. Okay. So let's read the problem statement again. An engineer who is designing a water toy is making preliminary calculations. A user of the product, whoever will be using this toy, will apply force F1 that moves the piston at a speed of 300 millimeter per second. So this piston will be moving at 300 millimeter per second, and the force will be applied F1. Okay, water at 20 degrees centigrade jets out of the converging nozzles. This is a converging nozzle here, and the water is going to come out in the form of a jet. Okay, of diameter 15 millimeter. To hold the toy stationary, the user applies a force F2 to the handle. So this is the handle with which the user holds the syringe, holds the toy in place. Okay. Which force, F1 and F versus F2, is larger? First of all, we need to find out which one will be larger. And explain your answer using the concepts of momentum principle. Then calculate F1 and F2. Neglect friction between the piston and the walls. Before moving towards solving the problem, the first thing is to understand the problem statement and the figure given in the problem. So is the problem statement and the figure given in the problem clear or not? If there is anything within the problem statement or the figure which is not clear, please feel free to ask. Good. Now let's start solving the problem. So if we, here in this problem, the force diagram and the momentum diagram are not drawn, but you are required to draw these two diagrams. Suppose if this problem comes in the exam. So suppose if this problem comes in the exam and any student exactly solves the problem the way it is solved here in the slides, without drawing the force diagram and the momentum diagram, then the points for the force diagram and the momentum diagram will be deducted from that student. Okay, so even it is not drawn here, you have to draw it. Okay, so it is now given in the lecture, so that when I deduct the mark in the finals, you know. Okay. So anyways, here we have, when we talk about the force diagram, so we have two forces here. We have the force, or one force that we are applying on the piston, the other force on the handle to hold, and obviously the two forces are opposite to each other. So summation Fx will be F1 minus F2. Okay, and then there won't be any accumulation term because the piston is not, or our toy is not changing its shape, is not actually expanding or contracting. Okay, at the same time, we have a steady flow throughout, so there is no flow variation with time. There is no there is no variation of density of the fluid with time. Density also remains the same. So there is no accumulation of momentum throughout. The momentum accumulation term will be 0. Now, if this is our control volume, so from our control volume, there is only one outlet. There is no inlet. There is only one outlet. So inlet term will also be 0. There won't be any inlet term. So summation Fx equals to m dot out v out. This is the equation that we are left up with, which is equals to F1 minus F2 equals to rho a v naught square. Okay, and the area will be pi by 4d square. So we know the density, we know the diameter. Obviously, the velocity is unknown, and these two forces are unknown. Okay, so this is unknown, and the velocity is unknown. Now, the second thing is that what we can do is that we can apply the continuity equation. So continuity equation says m dot 1 equals to m dot 2. Okay, 1 could be considered the point at the piston. Let's say this is point 1. 2 is the point coming out of the nozzle. Okay, so we have densities are going to cancel each other. So now we will have A1 V1 equals to A2 V2. A1 will be pi by 4 diameter of the cylinder square, into V1 will be velocity of the piston, and A2 will be pi by 4 small diameter of the jet square multiplied by the outlet velocity. So now we get a relationship between piston velocity and outlet velocity. Piston velocity was given in the question. So it was mentioned in the question that if the user applies the force such that the piston moves at 300 millimeter per second. So that was given in the question. So since we know the piston velocity, we can just substitute the value and we know the diameters. So we can find out what is the velocity at the outlet. So that's the velocity that comes out at the outlet. So once you have the velocity, now we can substitute this velocity into the equation here, and we can get what is F1 minus F2. Again, we don't know what is F1, we don't know what is F2, but we get a relationship here in this equation. Now, next thing is that we can apply the Bernoulli's equation. This time, velocities are something that we know, but we don't know the pressure. And why do we need pressure? Because we need the force. We need the force F1, we need the force F2. But force F1 is the force of the plunger, okay, or the force of the piston, okay, that depends upon how much will be the pressure of the piston. Okay, so right now we need the pressure to find out the force. Here we have the velocities. So Bernoulli's equation is actually equating the pressures with the velocity with the elevation head. So if two things are known, one thing is unknown, so you can find that unknown. So if you know the pressures, you can find out the velocity. If you know the velocities, you can find out the pressure, both way around. So here we are using it. The Bernoulli's equation we have at the piston point. At this point, let's say this is point 1 and this is point 2, we are using it. Obviously, there is no elevation difference, so elevation component Z will be cancelled. Okay, this is jet is going out into the atmosphere, so P2 will be 0. So we are going to end up with this equation. Okay, in this equation, we know the velocity of the piston, we know the velocity at the outlet, we know the densities. Only what is the pressure at the inlet of this nozzle. This is something that we can find out here. By substituting the values, we can find out what is P in. Now, if we know what is P in, okay, then we can find out the force, because force is equals to pressure into area. So we know the pressure, we know the area because we know the diameter now. So we can use this to find out what is force F1. So F1 comes out to be 182.4 Newton. Now we already have an equation where F1 and F2 are linked together. Okay, so if we know F1, we can substitute the value of F1 in this equation and we can find out what is F2. So F2 comes out to be 169.69 Newton. So it's very clear if we see the two forces, F1 is greater than F2, and that makes sense because the force which is required to push the plunger should be greater than the force which we are applying it on the support to hold the toy in place. Okay, because the force which is required to push the plunger is actually doing two things. One thing is it is pushing the fluid inside to go out of the nozzle, and the other thing is it is pushing the toy to move in certain place, okay, in certain direction. So the pushing of the toy is countered by the other force, but the forcing of the fluid to go out of the nozzle, this is actually used to push the fluid to go out of the nozzle. So F1 must be greater than F2. So this is the solution of this problem. So is there anything within the solution of the problem which is not clear to anybody? Please feel free to ask. Okay, next is the topic of vanes. Before starting the topic of vanes, let's have a break of 5 minutes or 5 to 10 minutes, and then we will be back with this topic. Okay, so now let's start with the next topic, which is about vanes. Vane is a structural component, typically thin, that is used to turn a fluid jet or be turned by a fluid jet. Okay, so vane is something that we encounter a lot throughout in our day-to-day life. For example, for example, these fans, the ceiling fan that we have the blades. The blades are the vanes. These are doing what? When the fan is running, its main objective is to take the air from upside and push it downside so that we can actually feel it. Okay. Sometimes the blades of the fan are not properly adjusted. So what happens is that you might feel that the fan is running, but you're not feeling any air because you want the air to be redirected to yourself. So the air is here, okay, but you want the air in at a comparatively higher velocity to be redirected towards yourself. Okay, so this is what is the main objective of the blade. It redirects the fluid. The fluid is there, it is moving, but you want to redirect the fluid to some place, okay, to some place at some point. And so this is being done by the vanes. So the blade of this fan, ceiling fan, are basically the vanes. Okay, when the fan is running, the objective is that it takes the air from the back and then redirect the air in such a way that it is distributed throughout properly in the room. So this is one thing. Then another thing is that, for example, if you look here, the split AC indoor unit, so you have vanes here. Okay, the vanes here are there at the exit, and you can close it, you can open it, you can redirect it so that the air of the air conditioner coming out is directed towards the ceiling. You can redirect it so that it is actually falling below or maybe at a certain distance. Okay, so just by setting the angle of the vane. Okay, so it is not like a blade of the fan, it is separate. It is not moving. In generally, it is stationary. Okay, the blade of the fan is actually moving. Okay, but this is also a vane, that is also a vane, that's a stationary vane, redirecting the flow. So it is positioned in a way such that whenever the fluid is flowing through it, passing through it, it is redirected to whatever the place you want it to be directed to move. So this is what it is. A vane is a structural component, typically thin, normally very thin. If you look here, the blade of the fan, they are thin. If you look there, the vanes of the indoor unit of the AC, they are thin. They are normally typically thin, that is used to turn a fluid jet. That's the main objective. You want the fluid jet to be redirected, to be turned, or to be turned by the fluid jet. Sometimes they get turned by the fluid jet as well. Like for the case of the turbines. In the turbines, you have the blade. So in that case, the fluid is actually turning the blades and rotating the turbine. Okay, so this is like for example, the blades of a turbine or a sail on a ship. Okay, so these are known as the vanes. In analysis, flow over a vane, the following assumptions are made. Constant fluid pressure everywhere. So the fluid pressure remains constant throughout, okay? Whether you have the flow inlet, whether you have the flow outlet, at any point, the fluid pressures are considered as constant. Elevation changes are negligible because the vane itself is comparatively very small, okay? The blade of the fan is very small. The vanes of the air conditioner are very small. So normally we consider that the elevation changes at the inlet and exit of the vane is almost negligible. So the elevation changes are negligible. Viscous forces are negligible. Therefore, according to Bernoulli's equation, the speed of the jet stream relative to the deflector surface remains unchanged. Okay. So Bernoulli's equation says what? Bernoulli's equation says that if the pressures are same, because there is a constant fluid pressure. Okay, you can see the Bernoulli's equation is P plus gamma Z plus rho V square upon 2. This is the Bernoulli's equation. We are saying that the effect of elevation is negligible. We are saying that the pressures are constant everywhere. Okay, so if this is true, that means the velocity at point 1 will be the same as the velocity at point 2. Okay, so we will get V1 equals to V2 equals to V3 throughout the fluid jet. The velocities across the vein remains same. Now this is one fundamental thing. For the case of veins, V1 is equals to V2 equals to V3. Whatever the fluid flow is there across the vein, they all will have the same velocity. Because whenever the problems of the vein will be given, you might have velocity at one point in the vein, and at the other points, the velocity might not be there. Presuming that you know that for the case of veins, the velocities are constant throughout. Okay. So this is, I have already mentioned. Okay. So now let's start and try to solve problem related to veins. So what are the kind of problems that we have solved yet? Initially, we started with jet, okay, the fluid jets. Then after that, we moved towards nozzles. And now we are discussing veins, okay? So this is vein, which is the third category of the type of problems that we'll be solving. Okay, so a water jet is deflected 60 degrees by a stationary vein as shown in the figure. So this was a water jet and it is deflected. How much is the deflection? Deflection is 60 degrees. Okay, by a stationary vein as shown in the figure. The incoming jet has a speed of 100 feet per second. So we know what is the velocity of the incoming jet. Okay, and a diameter of 1 inch. We know what is the diameter of the jet. Find the force exerted by the jet on the vein, neglect the influence of gravity. Obviously, when the deflector is there, the vein is like a deflector. So when it is deflecting the fluid, so there is some force which is being exerted by the fluid on the deflector. So we need to find out how much is this force. Okay, how much is the force exerted by the jet on the vein? Okay. We are neglecting right now the influence of gravity in this analysis. So that's the problem statement. Before moving towards the solution of the problem, first of all, do you understand the problem statement? MashaAllah, your understanding is very acute. So in order to solve the problem, the first thing is that we need to draw the free body diagram. In the free body diagram, we are going to draw the force and the momentum diagrams. Okay. So in the case of the force diagram, we are going to just discuss about the forces. So we have the fluid flowing, okay, and the fluid is flowing in this direction. So the forces here will be just the reaction force, which will be exerted over the support here. Okay, so that will be Fx component and Fy component. These are the two components of the forces. There are no any other force here in the system. Okay, then the other thing is the momentum diagram. In case of the momentum diagram, there is the fluid coming in to our control volume, which is m dot v, and fluid is going out of the control volume, which is m dot v. But it is deflected by an angle 60 degrees. So this is the momentum diagram. This is the force diagram. Now let's try to solve the problem. Okay, so we have this equation that we are going to use here. Summation F is equals to, first is the momentum accumulation term. Okay, so this term will not be there. There is no change in momentum with time. Okay, then we have the momentum of the fluid going out of the control surface, and then momentum of the fluid coming into the control surface. Okay, so let's talk about right now we are writing this equation in the vector format. So let's talk about the force vector. So the force vector will be summation F is equals to, okay, if we decide that the force directions will be as what shown in the figure, so we'll have negative Fxi, negative Fyj. So we'll have two components of the force here. Then the momentum accumulation term, first of all, that will not be there. Okay, so integral d by dt or the control volume rho v dv, this thing is equals to 0. Okay, then we will have the momentum outflow terms, and then we'll have the momentum inflow terms. We will have momentum outflow as well as we will have momentum inflow. Why? Because in this problem, okay, we have the momentum of the fluid coming into our control volume, and we will have the momentum of the fluid going out of the control volume. Okay, though going into the control volume will only have x component, it will not have any y component, but going out of the control volume is at an angle of 60 degrees from the horizontal, so it will have both x and y components. So let's discuss about the momentum outflow factor going out will have x and y component. Now, if you look here about the x and y component for the one going out, okay, so its x component will be in the positive x direction. X component will be in the positive x direction, but the y component will be in the negative y direction, given the positive x and y are corresponding to the x's drawn here. So we'll have m dot v cos 60, that will be the x component I, and it will be positive. And then we'll have a negative component m dot v sine 60j. Okay, so that will be in the negative y direction. So we'll have, this is the momentum outflow vector. Let's discuss about the momentum inflow vector. So inflow vector will have only in the x direction, because the fluid is moving only in the positive x direction. There is no component in the y direction. So correspondingly, we'll have summation m dot I vi will be m dot v in the I direction. Now mass flow rate. Mass flow rate is equals to rho AV. Now density is given, density is known for the fluid, okay, and area. Area will be, because we know what is the diameter of the jet. The incoming jet has a speed of 100 feet per second and a diameter of 1 inch. We know the diameter of the jet, so corresponding to the diameter of the jet, we can find out what will be the cross-sectional area of the jet. Okay, so it will be pi by 4 or pi r square, or pi by 4 into d square, okay, multiply by the velocity of the jet, since it is mentioned that for the case of the problem of vanes, the velocity at the inlet and outlet, all the velocities are same. And how do we know this? We know it from applying the Bernoulli's equation. And this is what I've already shown you before, that since it's all outside, so pressures are all same. And if the pressures are all same, and the component of elevation factor is very minimum, so the velocity components will always be same. So that's why the velocities are same. So we have the velocity of the jet. So correspondingly, we'll have the mass flow rate, and the mass flow rate will be mentioned here as 1.06 Sec per second. So now we can write our main equation in the form of I and j components. So negative fxi, negative fyj, that's the force component. And then we'll have the mass flow mass flow out minus mass flow in. So mass flow out will be m dot v cos 60 minus m dot v. So that will be, because you see here, this is the I component and this is the I component. Okay, so we just coupled the I component together. So m dot v cos 60 minus m dot v. The I components coupled together minus the j component. So here we have the j component in case of m dot out, in case of the momentum outflow, but there is no j component in the inflow. So we'll have just one component. Then we can separate it component by component. So we'll have the x component equation, we'll have the y component equation. Now the x component equation becomes like this. We have all the values here. We have m dot already calculated. We have the velocity of the jet. So just substitute the values. We can get the x component of the force. In the same way, we can find out what will be the y component of the force. If we have the x and y component of the force, we can write them together to find out what it will be the total force, magnitude of the total force. So this is the solution to this problem. If there is anything which is not clear to anybody, or anybody want to ask anything regarding any specific step regarding this problem, regarding the solution of this problem, please let me know. Everything is 100% clear. So then let's move over to the next problem. Force on an axisymmetric vane. Our question is that, do you know what is axisymmetric? Symmetry means similar, and axisymmetry means similar along the axis. So something is in a circular pattern such that if you just take one section of the axis, it is same throughout. So that is axisymmetry. Okay. So the force on an axisymmetric vane. So suppose we have a vane here as shown in the figure. This is a vane. So it's shown just like a section here because it is a side view, but it is actually circular. So as shown in the figure, an incident jet of fluid with density rho, speed v, and area a is deflected through an angle beta by a stationary axisymmetric vane. Find the force required to hold the vane stationary. Express the answer using rho, v, a, and beta. Neglect the influence of gravity. So beta is the angle with which the jet is being deflected, okay, and the velocity with which the fluid is coming towards the vane is v. Density of the fluid is rho, and the cross-section area of this jet is a, and beta is the angle of deflection of the jet. So we need to find out how much is the force required to hold it in place. Okay. Okay, so this is what we need to find. We need to find what is the force required to hold it in place. The most easiest thing to understand is that suppose if there was no support here, what would happen to the vane when the jet is going to fall on it? It will just go back. ठीक है, आपके पास एक वेन है, कोई प्लेट है, उस पे आप उसको छोड़ दें और उस पे जेट मारें तो जेट की वजह से वो प्लेन दूर जाएगा, प्लेट दूर चली जाएगी. लेकिन ये कि if we have a support here at the back, obviously the support is going to be then holding the plate in place. But we need to find out how much the force is required to hold it in place. Okay, this is what we need to find out. So obviously that the jet force is something that we need to calculate here. So here actually everything is in the form of variables. There are no values here in this problem. So obviously the solution would be in the form of variables. So let's go for the solution. Let's see the solution. Okay, so first of all, we draw the force diagram and the momentum diagram. When we draw the force diagram here, so obviously there is the weight of the fluid which is acting downward, and then there is a reaction force of this vane of the support, okay, which will be in the direction opposite to the jet. So these are the two forces that we are going to have. And the other way around, when we discuss the momentum diagram, so we will have, this is our control volume. Within our control volume, we'll have the momentum of the fluid coming in. And then we will have, now it's shown here as if it is going out from this side and this side, from up and down. No, it's not like this. This is an axisymmetric. This is axisymmetric. This is a dome shape. So when the fluid is coming over to it, fluid is deflected from all sides, okay, from the whole circle, okay. But obviously when you are looking from sideways, it looks like it is going up and down. It's not just going up and down, it's going all the way around. It's axisymmetric, same along all the axes or the entire axis, okay. So we have here like this. Okay. So first of all, we are going to have the equation here, because the force here, we need to find this force. This is the force that we need to find, okay? And this force here is very clear that it will be there only in the x direction. So just if we make the x component of the equation, that would be enough to actually find out this force. So x component of the momentum equation will be like this: summation fx equals to momentum accumulation term plus the summation of all the momentum coming into the control volume, sorry, going out of the control volume minus summation of all the momentum coming into the control volume. Okay, so first of all, momentum accumulation term is zero. Why it is zero? Because our control volume is fixed. The vane is not moving. The vane is not being displaced. The vane is not expanding, not contracting. So there is no momentum which is being accumulated inside the control volume. So with time, so momentum accumulation term is zero. So if we have the momentum accumulation term zero, let's look at the other terms. Let's talk about the forces. Since we are talking the forces in the x direction, so we have just this force. That's the only force we have. So summation fx equals to negative f. Now let's momentum accumulation term will be zero, so that's clear. Now let's talk about the momentum outflow. So momentum outflow is whatever the fluid going out of the control volume. So fluid going out of the control volume is from all sides. Okay, but it is the same fluid which is coming in, it's actually going out. So it's basically m dot v is something which is going out, but since we are talking about the x component, so and it is making an angle beta with the x-axis, so it will be m dot v cos beta that will be going out, but the x component will be in the negative x direction. So that's why a negative sign is here. Negative m dot v cos beta is the momentum outflow. Momentum inflow is the same fluid which is coming in, so it will be m dot v, and that's it. So momentum inflow is m dot v, momentum negative m dot v cos beta will be the momentum outflow. So now we have momentum inflow, momentum outflow, accumulation term, and summation of forces. Just substitute all this into the main equation. So this is our main equation. If you substitute all into the main equation, so the equation becomes this. Just simplify it a bit. So it becomes F is equals to m dot v 1 plus cos beta. Now m dot is basically rho AV. So if you substitute rho AV, it becomes rho AV square 1 plus cos beta. And this becomes the value of the force. Since there was no numerical value here in this question, it was just asked to find out F as a function of rho, A, V, and beta. And so we have already determined it. Now, what change I can do is that I can provide you this in this exam, in this problem, the same problem, but at the same time, I can add a part B that if the velocity is this thing and the area of the jet is this much and the angle of beta is this, determine what will be the force required in Newton or kilonewton. So here you already have determined the formula, just substitute the value in the formula and get the answer. So a little part could be added. Now here, one more interesting thing that could be done. Suppose if the vane was not horizontal, if the vane was vertical, then the component of weight would be added to it. Right now, since the vane is horizontal, so the weight is acting in the downward direction, but when we are making the x component of the equation, so the weight is not actually contributing into it. But suppose if I provide the same figure, but 90 degree in 90 degree, like this. So the jet is coming upward and then distributed by the vane like this. So in this case, what will happen? Our summation fx, or instead in this case it will be fy. Okay, so summation fy will be negative f, negative w. Then it will be like this. So only that thing. But in that case, I also need to provide you the weight of the fluid inside. Oh, I can provide you the weight of the fluid in the question. Okay, the rest of the equations would remain the same. Rest of the equations and everything else would remain the same. Okay, but this change would occur. So obviously, once this change occurs, so force on the vane will also change a bit because W will also come in this equation. Okay, or whatever the weight provided, you have to then add it into the equation. Okay, so anyways, this is also one modification that you should memorize or you should practice for the case of exam? So that was the solution of this problem. So the problem is done. Is there anything within the solution of this problem which is not clear? Please feel free to ask. Okay. So now let's move over to the next problem. So a planar water jet. Now this is important. When we are saying a planar water jet means you have a jet of water, but it is not circular. Normally, whenever it is jet of water, we assume that water is flowing, so it must be circular jet. But when we are saying planar water jet, it means it is not circular. It means the section is a plane. Consider it as a square or a rectangular jet. Okay. So a planar water jet, 15.5 degrees centigrade, is deflected by a fixed vane. So this is the vane that we have. Okay. This vane is fixed, so it's not moving. What are the X and Y components of the force per unit width needed to hold the vane stationary? Okay, neglect gravity. So it's like this, that 12 meter per second, with the speed of 12 meter per second, a jet is coming, and that jet is coming, that incoming jet is then deflected by this vane. Some part of it goes down, deflected down 30 degrees centigrade, sorry, 30 degree, and the other part is deflected at an angle of 60 degree. Okay, in the upward direction. Okay, so now we need to find out that how much is the force needed to keep this vane in place. Okay, suppose if this vane was not welded or supported by any means, so what will happen? This jet is going to take the vane with itself and will push the vane from its place. But if you want to hold the vane in place, you don't want the vane to move, you want the vane to remain stationary, then how much is the force needed to keep it in place? This is the question. Okay. Before moving towards the solution of the problem, first of all, do you understand the problem statement and the diagram? Okay. Now let's go for the solution of the problem. The first thing is that we draw the force diagram and the momentum diagram. So the force diagram is just, we'll have the Fy and Fx component of the forces needed to hold it in place. Then we'll have the momentum diagram, which shows that m.1 velocity v is coming towards the vane, and it is being deflected to m.2 v and m.3 v. Okay, so these are the two specific momentums going out of this vane. So first of all, if we apply the Bernoulli's equation, so based on the Bernoulli's equation, we already discussed that the velocities would remain same because the elevation factor head is all not there, and because it is atmospheric pressure throughout from point 1 to 2 to 3. So the only factor left is the kinetic factor, kinetic pressure factor, and so the velocities would remain the same. So V1 equals to V2 equals to V3 equals to V, which is 12 meter per second. So it's the same velocity throughout. Okay, now when we apply the continuity equation, okay, so continuity equation says that mass flow rate is conserved, so mass flow rate coming in equals to mass flow rate going out. So here the mass flow rate coming in is this one, m.1, and the mass flow rate going out will be m.2 and m.3. m.3. Okay, so here it will be what? m.1 is equals to m.2 plus m.3. Or since it is water throughout, so the densities will cancel. So we'll have A1 V1 equals to A2 V2 plus A3 V3. Okay, and these jets are the planar water jets. So it will have, you can say that each water jet has a component of height and width because they are basically rectangular section. So here we have the width and here we have the height. Okay, so we'll have the height and the width. So area will be height into width, and here the width is same, equal to the width of the vane. Okay, so W is same throughout. So the equation becomes WH1 V1 equals to WH2 V2 plus WH3 V3. WW's cancel throughout in this equation. So we'll get velocities are already same, V1, V2, and V3. So velocities can also be cancelled out, taken common. So what we are going to be left up with is H1 equals to H2 plus H3. And so height of the vane here is height of the jet here is given 3 centimeter. Height of the jet here is given 6 centimeter. So the height of this incoming jet will be 6 plus 3 equals to 9 centimeter. So we got this 9 centimeter. How? By first applying Bernoulli's equation, then applying continuity. So we apply these two equations, then we come up to this answer. Okay. So Bernoulli's equation and continuity equation. Now we come to know that what is the height of this jet. The next thing is that we can apply the momentum equation. Now the momentum equation there will be applied in the X and Y component directions. Okay, because the jet will have the X and Y components. Okay, momentum accumulation term will not be there, so it's not written here. Okay, but obviously in the exam, you have to first write the whole equation and then you have to mention that why momentum accumulation term is 0. And then you have to come up to this equation. So we have, this is the X component, summation Fx equals to summation of all the momentum of the fluid going out of the control volume minus summation of all the momentum of the fluid coming into the control volume. Okay, so summation Fx in this case here will be just negative Fx, no other force. Okay, and momentum going out of the control volume. So we have two momentums here, m dot 3v and m dot 2v. These are the two going out. So it's m dot 2v cos 60 because 2 is going at an angle of 60 degree from the horizontal, and we're talking about the X components. So cos of 60. And here for the case of m dot 3, it will be cos of 30, but in the negative X direction. Okay, so we'll have m dot 3 negative v cos 30. Okay, so this will be these two terms together will be m dot out v naught x. Okay, and then let's talk about the momentum coming in. So momentum coming in is only in X direction, positive X direction. So it's negative m dot 1 v. Now in this equation, when we talk about m dot, so m dot is equals to rho a v, right? And in this case, rho is there, is constant throughout. Okay, velocity is also constant because velocity at 1 and 2 and 3 are all same. This is the case for the case of vanes. It's okay, and area will be what? So area will be the cross-sectional area since these are the planar jets. So area will be A1 will be WH1, A2 will be WH2, A3 will be WH3. Okay, so if you just substitute the values of the areas, okay, so we are going to okay, what we need is, if you see in the problem, we need to find x, y component of force per unit width. Per unit width. So in this equation, if we substitute the values of area, A1, that will be A2, and here this one will be A3. So we'll have W in each of these terms, then, but we need Fx over W. So W can come over the other side of the equation. Okay, so the rest of the things all we know the heights, okay, we know the velocity, we know the density. Just substitute the values, you're going to get what is Fx per unit width. Okay, so this is actually determined. Now, once we have done for the case of X direction, then in the same way we can do it for the Y direction. But in case of the Y direction, there is no inlet component because the inlet component is only in the X direction. So the Y component for the Y direction, inlet component will be 0. So we'll have just this term, summation m dot o v naught y. So we'll have m2 v2 sine 60. Sine 60 will be in the upward direction, and here sine 30 will be in the downward direction. So it will be negative v sine 30. So again, substituting the values of the area, okay, and then we can find Fy over W. So that will be the force in the Y component of the force per unit width needed to hold the vane in place. So that's the solution of this problem. So the problem is done with its solution. If there is anything that you do not understand in the solution of this problem, please feel free to ask. The next is the last topic here, last application, which is in case of the pipes that we are going to cover. So before that coverage, let's have a break of 10 minutes, and then we are going to cover it. We already have about 1 hour, so probably we'll be able to do it within this time. So let's have a break of 10 minutes, and then we'll be back. Okay, so now let's start with the last application that we are going to be covering in the lectures of momentum equation, which is in the pipe flows or in the pipe bends. Whenever in the pipe flow, the assumption is made about the fluid flow through pipes are itemized as follows. It is usually assumed that the velocity is nearly constant across each section of the pipe. So let's say if I have a pipe, what we assume is that at any section, the velocity is constant. Okay. So this is the first assumption. And the force acting on a pipe cross section is given by PA. So at any cross section, whatever the force acting is given by, because it is a fluid force, so this force is equals to pressure multiplied by the cross-sectional area. And it is applied at the centroid of this cross-section. So these are the assumptions that we make for the fluid flow analysis in the application of momentum equation for pipes. Let's talk about pipe bends. It is a structural component that is used to turn through an angle. It is often connected to a straight runs of pipe by flanges. A flange is a round disc with a hole in the center that slides over a pipe and often welded in place. Flanges are bolted together to connect sections of pipe. Okay, so this is how the flanges are. Suppose we have a pipe bend. So what we do is that that pipe bend, and on both the ends of the pipe bend, we have the flanges. So we have a flange here, we have another flange here. So we have the pipes, and in the pipe we also have flanges. So what we do is that we mate the flanges of the pipe with the flanges of the pipe bend. Okay, and then we bolt them together. So the pipe bend is actually held together with the help of flanges with the pipe. Okay. So pipe bends are normally used to bend the pipe, but whenever you are actually redirecting the flow, so the fluid itself is going to impart a specific force over the thing which is trying to redirect the flow. So if the fluid was moving in one way and I put my hand in the path of the fluid, so my hand is going to face the force of the fluid. Okay. So while I'm trying to bend the motion of the fluid will try to bend my hand at the same time. So the same thing occurs here when the fluid is flowing through a pipe bend. The pipe bend is actually bending the motion of the fluid, but at the same time, the fluid is going to be exerting force over the pipe bend to push it out of the way. Okay. So the flanges are used to hold it in place. It's always better to have a good or a better visualization of the problem. So for that, I will request you to go on the YouTube and write down welding of flanges on pipe. So you can see that how the flange is welded on a pipe, okay, and then how it is connected to a pipe bend, okay, and connection of the flanges. So it will the picture would be much more clear to you when you see it on YouTube videos. Okay, so now let's have a problem here. A 1 meter diameter pipe bend, a 1 meter diameter pipe bend shown in the diagram is carrying crude oil. So it's a very big pipe. 1 meter diameter means that much height. Okay, this is a big pipe and it is carrying crude oil. Specific gravity 0.94. almost close to water. With a steady flow rate of 2 meter cube per second. So that's the flow rate through this pipe bend, 2 meter cube per second. The bend has an angle of 30 degree. Okay, so bend has an angle of 30 degree. Normally, how do we find out the bend angle? We look at the flow. Okay, so inlet flow was like this, outlet flow is like this. So we see how much is the angle between the inlet and outlet. And based on that, we decide that what is the pipe bend angle. Okay. So it has an angle of 30 degree and lies in a horizontal plane. So the pipe bend, 30 degree bend is there, but this whole bend is on a horizontal plane. Okay. The volume of the oil in the bend is 1.2 meter cube. So it's a very big bend, pipe bend, and so the volume of oil inside it is like 1.2 meter cube. And the empty weight of the bend is 4 kilonewton. So suppose if we have that pipe bend and there was no oil in it, then the empty pipe bend itself has a weight of about 4 kilonewton. Okay. Assume the pressure along the center line of the bend is constant. So along the center line, the pressure is constant throughout. That means whatever the pressure I have at any point, it is constant. So this is my center line. So this will be my center line. So pressure across this center line is constant. So whatever the pressure I have here is the same as pressure here, same as pressure here, same as pressure here. This is just an assumption. In reality, there will be pressure variation to make the pipe to flow, to make the fluid to flow inside the pipe bend. Okay. But anyways, for this problem, we can assume that there is no pressure variation throughout. The pressure is same. With a value of 75 kilopascal gauge. So the gauge pressure is provided, which is 75 kilopascal. Find the net force required to hold the bend in place. We need to find how much is the net force required. F required to hold the bend in place. Obviously, if the pipe bend was not flanged together with pipes, then as the fluid flows through the pipe bend, it will push the pipe bend out of its way. So when it is flanged with the pipes, now it cannot move away, but the flanges are now actually holding the pipe bend in its place. And when these flanges are holding pipe bend in its place, obviously some force is applied to keep it in place. So we need to find out how much is that force. Okay. So this is a problem. We have a very big pipe bend, 30 degree angle, and it is lying horizontally. So like, for example, on, let's say, on the floor. So 30 degree angle is not vertical. That's horizontally 30 degree angle. Okay. And volume of oil in this bend is about 1.2 meter cube. The empty weight of this bend is 4 kilonewton. The flow rate through this is steady. Steady means no momentum accumulation term. Okay, that's 2 meter cube per second. And the pressure along the center line is fixed. It's constant. It's about 75 kilopascal gauge. We need to find out how much is the force required to hold the bend in place. Okay, so this is the problem statement, and this is the figure of the problem. First of all, do you understand the problem statement along with the figure? Is there anything within the problem statement or the figure which is not clear to you? Please feel free to ask. Okay. So let me just draw it here. This is the inlet. This is the outlet. So when outlet drawn with the inlet, the angle is 30 degrees. Okay. So I drawn it here because I have to rub it from here. Okay. So now let's move over to the solution. In order to have the solution, the first thing will be to draw the free body diagram. So that means we need to draw the force diagram and we need to draw the momentum diagram. Okay, when we have to draw the force diagram, so there is fluid on this side, there is fluid on this side. I mean, on both sides of the pipe bend, we have fluid. Okay, so we are going to have the fluid force of the fluid on both sides. Okay, so we have PA is the force of the fluid going on this side. We'll have PA, the force of the fluid going on this side, applied on this side. Okay, since the pressure is same and the cross-sectional area is also same because the diameter of the pipe is not changing, so that will be the same force on both sides. Okay, the other thing is that we'll have the reaction forces on the flange. Okay, I can consider any one of the two flange, and we are going to have the reaction forces, and these are the reaction forces that we need to find to hold this pipe bend in place. Okay, so suppose this is in the horizontal plane XY direction. Okay, so on the X, let's say X is now one side of the horizontal plane, the Y is the other side of the horizontal plane. Okay, so we'll have Rx and Ry are the reaction forces on the flanges that we need to find. But we also need to tell you that there is also weight of this flange. There is also weight of this pipe bend with the crude oil inside it. And the weight will neither be acting on the X plane nor be acting on the Y plane. It will be acting on the Z plane because XY is the horizontal plane. XY is the horizontal plane, but weight is not going to act on a horizontal plane. Weight is going to act vertically downward. So it will not be X and Y, it should be the Z plane. So weight is acting in the Z direction if the Z is downward. Okay, and X and Y are both horizontal. Okay. So in this problem, we are going to have X, Y, and Z, all three components. Okay. And the key was that, the key for this to understand is that this pipe bend lies in the horizontal plane. This shows that we are going to have the X and Y component, but the X and Y are both in the horizontal plane. So if the weight has to be considered, it has to be the third axis. So we are going to have all the three axes in our problem solution. Okay. So this is one thing. Then the other thing is that we are going to have the momentum diagram. In the momentum diagram, we have just one inlet inside this pipe bend and one outlet from the pipe bend. Okay, so m dot v is going into the pipe bend, m dot v is also going out of the pipe bend. And this is steady flow, so the same momentum is going into the control volume and same momentum is going out of the control volume. So now let's start solving the problem. The first thing is that we need to write down the equation, momentum equation for the fluid flow analysis. So that will be summation F is equals to momentum accumulation term. So, but this term will be 0 plus all the momentum of the fluid going out of the control volume minus all the momentum of the fluid coming into the control volume. Okay. So now let's see each of these terms one by one. So if we are talking about summation F, so summation F will have X, Y, and Z components. So let's talk about the X component. So in case of the X component, we'll have Rx. This is one force. Then we will have PA is also in the X direction. Then we will have this PA, and it will have a component in the X direction. Means cos 30 will be in X direction, but it will be in the negative X direction. Okay. So we'll have three forces here. Rx plus PA minus PA cos 30. Okay. So these will be the three in the X direction. Let's talk about Y direction. So we'll have Ry in the Y direction. This is in the X direction, so it's not there in the Y direction. But here, this PA will have a component in the Y direction. It will be in the positive Y direction. Okay. So we're going to have Ry plus PA sine 30 J component. And let's talk about the Z direction. In the Z direction, we don't have PA, but we'll have the weight. Okay. And if we are saying that Z direction upward is positive, so the weight will be acting downward. So it will be negative. Okay. So it will be RZ minus W in the K direction. Okay. So this becomes the vector format of the summation of forces equation. You can write it as Fx, Fy, Fz, or you can write it all together as I, J, K components. It's up to you, but both are okay. Is this equation clear? Now we move towards the second thing, which is momentum accumulation term, that is zero. Already discussed about it. Now momentum outflow. Now outflow will again have two components, I and J components, okay? Because if you look here, the outflow is at an angle. This is the outflow, it is at an angle. So it will have a positive X component and a negative Y component. So we'll have positive X component, negative Y component. Okay, that will be for the case of outflow. For inflow, it's just the positive X component. Okay, so let's have a look at it. So momentum outflow, m dot v cos 30, that's the positive, and minus m dot v sin 30, that's the negative component. So that's outflow. For momentum inflow, that is m dot v I, just one. Okay. So now we have the momentum inflow, momentum outflow, momentum accumulation, and summation of forces term. We just need to put all of them together in one equation. So that becomes one very big equation here. Okay, now what we need to do is that we need to separate the I, J, and K components. So if I separate the I component, so that becomes one equation, J component, that becomes another equation, K component, that becomes the third equation. Okay. Okay, so now what we need to find out, the pressure force PA, since the pressure was given in the question, and area, we know the diameter of the pipe, so we can just substitute the values, we can find what is PA. Fluid speed is the velocity. We can find out the velocity since we know that Q is equals to AV. Okay, so Q is given in the question, and area we know, because we know the diameter, we can find out the velocity correspondingly. And also we can find out the mass flow rate. Okay, so this term, momentum flux term, m dot v. Okay, so m dot v is, because m dot is rho q and v is v. So you can do it like this, or rho q is av. So it's, you can say rho av square. So they are both the same thing. So you can just substitute the values in here and find out m dot v. So now if we substitute everything into the equations in the x, y, and z components, we can find rx, ry, and rz components. Okay, rx, ry is done. But for the rz component, we need weight. Now, how can I find weight? So weight will be the weight of the oil plus weight of the pipe bend. So weight of the empty pipe bend was given, 4 kilonewton. Now, what about the weight of the oil? For the case of the weight of the oil, we have the specific weight of the oil multiplied by the volume. Okay. The specific weight of the oil, how do we know it? Because we know what is the specific gravity of the oil. So specific gravity of the oil multiplied by the specific weight of the water. So we're going to get the specific weight of the oil. Then this multiplied by the volume of the oil. So we're going to get what is the weight of this oil. So W equals to this gamma V, okay, is basically the weight of the oil plus weight of the pipe bend. Altogether, you're going to get what will be the weight in the Z direction. So here we have the reaction force. The components of the reaction force will be this much in the in the X direction, this much will be in the Z in the Y direction, this one will be in the Z direction. So this is the solution of this problem. If there is anything within the solution which is not clear, please feel free to ask. Now think about one thing. If I provide the same problem, no change in the problem statement, but there is only one small change if I make. If I just write here, instead of horizontal plane, instead of writing horizontal, if I just use the word vertical. then what will happen? In that case, weight will be added in the y direction, or you can say in the z direction. So you'll have just x and z. There will be no component in the y. Okay. So this will be a very small change, but something good to check the understanding of the strokes. Okay. So think about it. Okay. Because whenever I have the final exam, I have to make some changes. But as I told you, that I will not be surprising you if you have watched the lectures or gone through the lectures. Then you won't be surprised. Yeah. If you're not gone through the lectures, then maybe a little surprised. Okay. And normally the change that I want to make is such that the students do not feel that there is a change. Okay, so make sure that whenever you have problems in the exam, you read the problem statement very carefully, because it looks like that it is the same problem, but I have made a very minor change, but it is there. Okay. Okay, so let's discuss about this problem. It's again a similar problem, but this time I'm going to go a little bit faster because it's the same problem solution procedure. Water flows through a 180-degree reducing bend. So this is a 180-degree bend. Okay, so you can see here the flow was coming like this and then moving like this. 180-degree bend, and it is a reducing bend. So the diameter at the inlet was like 30 centimeter. Diameter at the exit is 15 centimeter. Okay. The discharge is 0.25 meter cube per second. So that's Q, and since Q is going to be same throughout. Okay. And the pressure at the center, okay, this is Q. And the pressure at the center of the inlet section is 150 kilopascal gauge. So this is 150 kilopascal, but where it is? This 150 kilopascal gauge is at the inlet section. This is the inlet section, 1. If the bend volume is 0.1 meter cube, so the bend is from here, from 1 to 2. This is the bend. This is the bend. So if the bend volume is 0.1 meter cube, so the volume is given, it is assumed that the Bernoulli's equation is valid. What force is required to hold the bend in place? So how much is the force required to hold the bend in place? Obviously, because of the fluid motion, there will be some force needed to hold the bend in place. Otherwise, the bend will move this way. Okay. The metal in the bend weighs 500 Newton. So that means the empty weight of the bend is 500 Newton. The water density is 1000 kg per meter cube. The bend is in the vertical plane. Now, this is the case when it is in the vertical plane. Okay. So this is the problem statement. First of all, do you understand the problem statement and the figure? Is there anything within the problem statement and the figure which is not clear? Please feel free to ask. So now let's move over to the solution. The first thing is that we need to draw the free body diagram. So we have the force diagram and the momentum diagram. In the force diagram, we will have, this is our control volume. This our pipe bend is our control volume. So we have a force of the fluid, okay, at the inlet, which is P1A1, force of the fluid at the outlet, which is P2A2. Okay. And we are going to have the reaction forces, Rx and Rz. Here we have said this is the X component, this is the Z component. So we have Rx and Rz reaction forces that we need to find. Okay. And obviously there will be the weight which will be acting in the Z direction, negative Z direction, but there will be two weight of the fluid plus weight of the empty pipe bend. Okay. So there are two weights here, weight of the bend plus weight of fluid, both acting downward. Okay. So this is the force diagram. Now let's discuss about the momentum diagram. So there is only one fluid inlet and there is one fluid outlet. That's it in the momentum diagram. So once we have the force diagram and the momentum diagram made, next thing is that what we can do is that we can write down the equations. So the x component of the equation and the z component of the equation. Okay. So then we can individually solve for each and every component. Let's talk about summation fx. So summation fx will be P1A1 plus P2A2. We have two forces, and then we'll have the Rx. These are the three forces in the x direction. In the z direction, we have Rz, and then the weight of the bend plus weight of the fluid. But Rz, let's say we are given in the upper direction, then both the weights are in the downward direction. Okay, so Rz minus Wb minus Wf. So we have this as the equation of summation f. Momentum accumulation term is 0. Okay, so both in the x component and the y component both are 0. Momentum outflow. Okay, momentum outflow will be, okay, if I look here in this diagram, so inflow will be in the positive x direction and outflow will be in the negative x direction. Okay. So momentum outflow is in the negative v2 direction. Momentum inflow is in the positive v1 direction. Okay. So both x components. In the z component, there is no inflow or outflow. Okay. So z component is 0, z component is 0. Okay. So now, since we have all the momentum inflows, outflows, accumulation terms, summation f terms, so what we can do is we can just add them together or substitute it into the main equation, main momentum equation for the x direction and for the z direction. So when we do it for the case of x direction, we got this equation. And when we do it for the z direction, we got this equation. Now here in this equation, we need to find out the velocities, v1 and v2, since we know the flow rate. Okay. So flow rate is Q, and Q is the same as Q1 or is the same as Q2. Okay, and which is basically A1 V1, which is equals to A2 V2. Okay, so we can find out how much is V1, how much is V2. V1 is Q upon A1, V2 is Q upon A2. Areas we know because we know the diameters. And Q was given in the question. So just substitute all the values, you're going to get what is V1 and V2. Then we can apply the Bernoulli's equation to find out what is the outlet pressure. Inlet pressure was given P1. So this pressure was given in the question. Okay. Velocities we have determined. Okay. Z component. Okay. Let's talk about the Z component. How much is the Z? Well, we don't know what is Z1. We don't know what is Z2. But we can find out what is the difference between 1 and 2. How much is the difference between 1 and 2? So let's have a look at it. Okay, check this figure out. Here, Z1, because this is in the vertical direction, so we cannot ignore the Z1 minus Z2 component. The Z1 and Z2 are not on the same point, in the same elevation. There is elevation difference. So Z1 elevation will be the center of this inlet point. Z2 will be the center of this point. So how much will be this distance? This is 15, so it should be 7.5 plus 10, and this is 30, so half of it will be 15. 15 plus 10 plus 7.5. So this will be how much? 25 plus 7, 32.5 centimeter, right? So look here. Z1 minus Z2 is 0.325 meter. It means 32.5 centimeter. Okay. So now we know everything here. Just substituting the values, we're going to get what is P2. So we can now find out the pressure forces P1 V1 and P1 A1 and P2 V2, P2 A2. So substituting the values of the momentum flux, we can get the X component and Z component of the forces. So I can make this change in this problem that instead of asking you to solve it as if it was in the vertical plane, I can ask you that the bend is in, instead of written vertical plane, The bend is in horizontal plane, right? You get the idea. Bend is in horizontal plane. Then what will happen? Weight will not be added in the Z component. Okay. So you'll have X and Y component and the weight will be only in the Z component. Like we did in the last one. So previous question, I can do it in this format, and this question, I can do it in the previous format in the exam. This won't be a bigger change. This won't be really something that is not doable, but will need your little attention in the exam to solve the problem. Okay. And you can try this on your own before the exam as well. Okay, so with all this done, we have the next topic, which is the Navier-Stokes equation, and it's basically the last topic. Now, the derivation of Navier-Stokes equation is something there in the lecture slides, as our explanation is given in the book as well. I don't want to go through it with you right now, but it is a part of the course, so you should go through it yourself. Okay. But the only thing that you should know from the short questions point of view is, what is Navier-Stokes equation? So the answer is that Navier-Stokes equation, the differential form of momentum equation. What is Navier-Stokes equation? It's a differential form of momentum equation. Now, what we have been doing was the integral form of the momentum equation. If we write the same equation, momentum equation, in the differential format, then this is given the name Navier-Stokes equation. This is the only thing that you should memorize for the short questions or conceptual questions point of view. Like 1 mark question. What is Navier-Stokes equation? The answer would be differential form of momentum equation for fluid flows is the Navier-Stokes equation. That's the answer. As simple as that. So I'm not going to ask you the derivation of this and any problems associated with it. So I'm not going to ask this thing. But it is obviously a part of this course. So you, being more enthusiastic, of course, you should go through it. With this, our chapter is done, and we have some homework problems associated with this chapter, chapter number 6. Okay. So we started from chapter number 1, then we are done with chapter 2, then we did with chapter 3. By chapter 3, you already given the midterm exam till chapter 1, 2, and 3. Now we have also done chapter number 4, 5, and today we are also done with chapter number 6. So from your textbook, we are already done 6 chapters. Okay. So if anybody have anything to ask, you can ask. Otherwise, the lecture is over and you can leave. That's it for today.